Good morning. I am Dr.S.Sivadevi, retired HOD of Physics, SFR College for Women, Sivakasi. This presentation is on rotational fine structure in electronic spectroscopy. Any spectral study probes into the structure and nature of bonding in molecules. The electronic spectrum is due to transition of electrons from one orbital to another orbital. The electronic spectrum is not a simple one. It has a complex structure. In the electronic spectrum of molecules, the spectral line has one or more convergent lines, and this is called co-structure. The co-structure is due to the vibrational changes of the molecules. The co-structure is broad and diffuse, and under high resolution, very close lines can be observed in each structure, which are due to the rotational changes of the molecules. These structures are called fine structure. So, the electronic spectrum has vibrational core structure and rotational fine structure. Unlike rotational spectroscopy and vibrational spectroscopy, all molecules show electronic spectrum because there is no condition like possessing dipole moment or possessing change in dipole moment is imposed on the molecules. So, almost all molecules show electronic spectrum. In order to explain how the rotational energy affects the electronic spectrum, we consider the Born-Oppenheimer approximation for the total energy of the molecule, which is given as E total is equal to E electronic plus E vibration plus E rotation. This equation is expressed in joules. You all know that E rotation is very small when compared with E vibration, and E vibration is very small when compared with E electronic. We can also write epsilon is equal to the energy E divided by hc, where h is Planck's constant and c is velocity of light, so that epsilon is expressed in centimeter inverse 1. And so the wave number can be represented as nu bar, which is equal to delta epsilon. For electronic spectrum, epsilon total is equal to epsilon electronic plus epsilon vibration plus epsilon rotation. We know that epsilon rotation is bj into j plus 1. We are neglecting the centrifugal stretching here, and changes in the total energy may be written as delta epsilon total is equal to delta of epsilon electronic plus epsilon vibration plus delta of bj into j plus 1. And the wave number of the spectral line can be represented as nu bar spectrum is equal to nu bar for electronic vibration transition from V prime to V double prime plus delta of bj into j plus 1. The first term nu bar V prime V double prime represents the electronic vibration transition, and it is the band origin. In order to know the spectral line or the wave number of the spectral line, the selection rule used is delta J is equal to plus or minus 1 only for sigma to sigma transition. Sigma transition is from the orbit which is nearer to the nuclei, so from s orbital to s orbital. For other transitions, say from s to p orbital or p to p orbital, delta J is equal to 0 or plus or minus 1. You know that delta J is equal to minus 1 for p orbital and delta J is equal to plus 1 for r orbital. So for sigma to sigma transition, you have only p and r branches. For other transitions, delta J is equal to 0 corresponds to q branch, and delta J is equal to minus 1 corresponds to p branch. Delta J is equal to plus 1 corresponds to r branch. So for other transitions, we have Q, P, R branches. For other transitions, another condition is imposed that J is equal to 0 to 0 transition is not allowed. Now, the wave number for the spectrum can be rewritten as nu bar spectrum is equal to nu bar V prime V double prime plus B prime into J prime plus 1 minus B double prime J double prime into J double prime plus 1. You have to note that the B value is not same in the upper electronic state and in the lower electronic state. B prime and J prime refer to the upper electronic state and B double prime and J double prime refer to the lower electronic state. Why B value is not same in all the electronic states? This is explained by the Frank quantum principle, according to which the equilibrium internuclear distance is different for different electronic states. Since moment of inertia depends upon the equilibrium internuclear distance, moment of inertia is different in different electronic states. Since B depends on the moment of inertia, B is different for different electronic states. B is inversely related to the moment of inertia. So if the moment of inertia decreases, B value increases. If the moment of inertia increases, B value decreases. So B value is not same in upper electronic state and in the lower electronic state. Let us represent B double prime for lower electronic state and B prime for upper electronic state. Now there are two possibilities. B prime is less than B double prime and B prime is greater than B double prime. Under what situation B prime is less than B double prime? One situation is if the electron excited is in a bond between the nuclei, that is in the s orbital, the bond in the upper state is weaker and so the internuclear distance is large and the equilibrium moment of inertia of the upper state is large and so B prime is less than B double prime. Whereas in antibonding orbital, B prime is greater than B double prime. Let us consider the situation B prime is less than B double prime and analyze the different branches. Apply the selection rule delta J is equal to minus 1 which corresponds to the P branch. So when you apply delta J is equal to minus 1, then the wave number of the P branch spectrum, which is nu P bar, is given as nu bar V prime V double prime minus B prime plus B double prime into J prime plus 1 plus B prime minus B double prime into J prime plus 1 the whole square. Now, if you apply the selection rule as delta J is equal to plus 1, we get the wave number for all branches nu R bar, which is equal to nu bar V prime V double prime plus B prime plus B double prime into J double prime plus 1 plus B prime minus B double prime into J double prime plus 1 the whole square. Here J double prime run as 0, 1, 2, 3 and so on. These two equations can be combined into a single equation by putting J double prime plus 1 or J prime plus 1 as M and rewritten as nu bar PR is equal to nu bar V prime V double prime plus B prime plus B double prime into M plus B prime minus B double prime into M square. The first term nu bar V prime V double prime represents the band origin. The second term B prime plus B double prime into M and the third term B prime minus B double prime into M square decides in which side of the band origin the branch will be occurring. For example, when you put M is equal to minus 1, then it is the P branch. So, when M is minus 1, the second term B prime plus B double prime into M becomes negative and the third term B prime minus B double prime into M square, that is also negative. So when both the terms are negative, the P branch wave number will be less than the band origin. So in the figure, if this is the band origin, the P branch lines occurs to the left of the band origin. As the M value increases, the line separation goes on increasing. We say that the P branch lines are diverging lines. Now if you put M is equal to plus 1 in the equation, then it corresponds to the R branch. In this case, the second term B prime plus B double prime is positive. Then the third term B prime minus B double prime is negative. But this third term is small. Even if it is negative, the term is very small because B prime is only few times lesser than B double prime. So the third term is small. The second term is positive, but it is large. So the second term plus third term is positive. So nu R is nu bar plus a positive term. So the wave numbers of R occurs to the right of the band origin. This is the band origin and the wave numbers occurs to the right of the band origin. As the value of M is increased, the line separation goes on decreasing, and for a particular value of M, the wave number is maximum, and after that when M is increased, the lines are degraded towards the lower wave number side. Also you can see that the line separation goes on goes on decreasing as M value is increased, and at this point the the wave number is maximum and it is called band head. So the band head occurs in the R branch. When you consider the Q branch, nu Q bar is nu bar plus B prime minus B double prime into J prime plus B prime minus B double prime into J prime square. So here both the terms, the second term is negative and the third term is also negative because B prime is lesser than B double prime. So the Q branch occurs to the left of the band origin, and as the value of M is increased, the line separation goes on increasing. We say that the Q branch is diverging towards left. The next picture shows the total spectrum. The first spectrum corresponds to the R branch. It is to the left of the band origin. It is converging towards the higher wave number side. We say that it is degraded towards red because red corresponds to higher wave number side. The P branch is occurring to the left of the band origin. It is diverging. The Q branch also occurs to the left of the band origin and it is also diverging. And the last graph is for P, Q and R branches combined together. This represents the band origin and this represents the band head. Now consider the case B prime is greater than B double prime. When B prime is greater than B double prime, the same equations are used to calculate the wave numbers, and it is found that P branch is in the low frequency side and shaded towards the violet. Since it is shaded towards the violet, the band head occurs in the P branch. R branch is also in the high wave number side, but the separation goes on increasing. Q branch is spread to high wave number side and the separation goes on increasing. So normally in any one electronic transition, All the vibrational bands are shaded in the same direction. Different electronic transitions may show different shadings. The shading towards violet or shading towards red tells about the B prime and B double prime values, and the observation of shading may assist in the analysis of the complex electronic spectra. So in this presentation, you have seen how the rotational effect of the molecule affects the uh, spectrum of the electronic transition. The effect of rotational changes on the electronic spectrum of molecules. Thank you.